that other word. First off, pronunciation. I say centripetal, centrifugal. Sometimes it's very difficult to understand which one I'm saying. So some people will go centripetal, centrifugal, which also seems to be a British versus American thing. Centrifugal, centripetal, fine, it's very clear. I'm just out of habit. Centripetal, centrifugal. If in doubt, this is the one I'm saying, most likely. In terms of meaning,
Center. That means escape or run.
or flee. Yeah, what English word do we have that has the same
Flee.
base?
Fugitive.
Yeah. So center fleeing. So a centrifugal acceleration of force would be away from the center. Centripetal, got the PET there, meaning seeking. And what English word do we have with that as in there, meaning basically from the same root? Alvin, it looks like you're about to say something.
I mean, part of me is like petting. Like, I seek pets. But the other part of me is like
I don't think that's the same root, but it could be. If you have two,
I took Latin and I like animals, so,
Okay.
you know,
sure,
ADHD is going, yay.
possibly. If you have two teams who come together, they seek each other out to compete, competition. So, when is it appropriate to use this? All right, so if I'm swinging something around on a string, so this thing is swinging around, if I look at the forces acting on this, on the bob here, I'll have a tension pointing towards the center. That is a centripetal force, centripetal force. If you do the force diagram of the string also, well, then there's a force pulling out like that. That's also the tension. Newton's third law still holds. So that would be a centrifugal force acting on the string, a centripetal force acting on the object.
Centrifugal is FT going towards it.
Centripetal, this would be centrifugal and centripetal.
Okay.
But typically, centrifugal or centrifugal force is used in a rotating reference frame. You're in the car and you're going around a curve, it feels like you're being thrown to the outside. In reality, if you're in a car and the car's going around a curve, your body just wants to go straight and the car is cutting you off. Every time you try to get out, it just pulls you back in. Godfather 3 reference.
Unless something's seriously wrong.
And so from looking at it from the Earth's point of view, in the non-accelerating frame, they were actually being pulled inwards. But in the rotating reference frame, so you're in a reference frame that is accelerating, then it feels like you're being thrown out. So sometimes textbooks will call centrifugal force a fake force, like the Coriolis force. Just forces that appear to be there if you're just dealing in something that's rotating from your point of view. All right, now that I suspect is the last time we will use that term unless one of you brings it up.
Watch me.
Yeah, I had you in mind. All right, so this will be the word I'll be using. Centrifuges, by the way, I think should be called centripetes, but I was not consulted. All right, I know what you're thinking. Hey, this is great, but where's the problems? Where's the math problem? I need some numbers. I need to use my calculator. Let's make that dream come true. All right, so when we do F-tong, we're not adding a new force to that. The centripetal force is going to be some combination of the forces we've already dealt with. So let's start out with a nice simple example of, I have a table, so side view. There's a hole in the middle. I have a mass swinging around in a circle on top of this frictionless table. And I have another mass hanging down here. Let's say this is a 3 kilogram mass and a 2 kilogram mass. The distance from the center to the center of mass of my swinging mass here is 1.5 meters. So S equals mu sub K equals 0. This is an equilibrium, static equilibrium. An overhead view.
Could you remind me what static equilibrium is again?
Not moving.
Okay.
Equilibrium, not accelerating. Static, not moving. Overhead view. We have an object here that is spinning around, attached to a string. So when you are doing a force diagram of this, obviously how you draw it depends upon where it is. I mean, if it's off to the right-hand side or left-hand side, that's most convenient, but if it's here, on this side of it as it spins around, well, then you still have to somehow write in vectors that are going away from you. And there's a way of doing that, but not particularly convenient. So what I'm going to do is do the force diagram when it is on the far right, as it spins around, far right from your point of view. What are the forces acting on the swinging mass?
And it's the 3 kg box?
Sorry, what was that?
The swinging mass is the 3 kg box?
The swinging mass is the 2 kilogram.
Oh.
The 3 kilogram is not moving.
How is the 2 kilogram moving?
It started moving and kept going.
Frictionless again?
Yep, that's this right here is to indicate frictionless.
Right.
What was your original question?
Force diagram, we're gonna figure out something about this. I guess figure out how fast it's going. What is the speed? What speed does the 2 kilogram mass need to go in order for the 3 kilogram mass to be in equilibrium?
It's not static.
3 kilogram mass is static.
You said equilibrium. Does that mean static or kinetic in this case?
Well, okay. I figured static was already given, but yes, how fast does the 2 kilogram mass need to go in order for the 3 kilogram mass to be in static equilibrium?
Okay, thank you.
The other indication that it would be static is the fact that I gave a distance here of 1.5 meters, and I did not give any indication that that was going to change. So if that distance stays the same, then that distance has to stay the same. So this is not moving up or down.
Okay.
Ideal room. All right, forces acting on the 2 kilogram mass. We'll just put a little 2 there so that we know which one we're talking about.
Tension.
Going,
That would,
all right, tension.
there's a normal force. It's pushing up on gravity.
We can do better.
Force little g.
That's acceleration.
Force of gravity.
What'd you say?
The force of gravity.
Okay, otherwise known as,
Big G? No.
Wait.
Wait.
yeah,
Oh.
wait.
Okay, so
Force of gravity is fine. All right, so we got those forces acting on the 2 kilogram mass. let's see the 3 kilogram mass here. What are the forces acting on the 3 kilogram?
Tension.
All right.
There's force of gravity. Away.
I guess I need a subscript there. W2 and W3. All right. So I have the force diagram done. Acceleration. What is the direction of acceleration at this point of the 2 kilogram mass?
He said it was acceleration,
Direction of tension.
Pardon?
In the direction of tension?
Yes. How'd you come to that conclusion?
Because the rope is pulling it inwards to keep it while it's, you know, to keep it from flying off.
Yeah. So it's traveling in a circle. The acceleration is towards the center of the circle, which would have to be that way. Or these two are balancing each other out. It's not coming off the table or digging into the table. And so those would balance. This is the unbalanced force. It'd have to be to the middle also. So my acceleration is that way. What about for this one? What's the direction of acceleration?
None, it's static.
All right. What was that, Ash? That might answer the next question, but Talon, you said
None? 'Cause it's
none.
static.
Why is there none?
Because it's static. Static equilibrium.
Ooh, yeah, the equilibrium part, not the static part. Equilibrium, acceleration is 0. And I've done that on tests where I say something's in equilibrium and then go through a bunch of questions, and the last question is, what's the acceleration? And immediately, equilibrium, 0. All right, coordinate axis. So one of them in the direction of acceleration, one perpendicular, so that one we can establish. So I'm gonna make I hat and J hat. And on this one, acceleration is 0, so it's either up or down is positive. It doesn't matter which one you pick. Pick one. Anyone with a preference? And we'll make that the I3 hat. And I'll just leave that as is. Okay. Coordinate decomposition. Do we have to break anything up? Ava, I'm seeing head motion there.
No,
Nope.
I don't think so.
And Abigail? You had none? Okay. It seems to be a groundswell of 2 people. You're correct. Equations of motion. What are the equations of motion? First, how many equations will we have?
3.
Yep. So I'll have an I hat. Oops. I'll have an I hat, a J hat, and an I3 hat. Somebody give me one.
Weight times sine theta minus
Wait, which one are you doing?
I3.
I3, okay.
Sorry, no, I'm looking at it from. Yeah, there's weight and there's force.
So I have the tension.
You up here? Okay, tension.
And then that'll equal mass. What's it? And acceleration. So
Okay. It is mass times acceleration, but because we know this is centripetal acceleration, I'm gonna put a little subscript C there, just to indicate it is centripetal acceleration.
Dr. Fox, would we put mass 2?
Yes, thank you, has to.
Can you put that on the I and J as well?
Not necessary, but,
It'll help me.
okay.
The J hat 2 is normal force minus weight 2 equals mass 2 times acceleration. Is centripetal.
So it's traveling in a circle like this?
No, I lied, but I don't know.
What is the vertical acceleration?
Zero.
Zero.
Sorry. Forget everything.
And again, the point of setting up our coordinate system the way it is so that one of these equations is equal to 0. All right,
Tension minus weight equals mass times 0.
substitution. For what do we have an independent formula?
Wait,
And
and Y?
And tension, right?
the tension is always problem specific.
Yes.
This is the new one. This is why this is part of chapter 6 and not 5, 4, or 5.
Acceleration.
Yes, we have an independent formula for acceleration, because it's centripetal acceleration. So we do the substitution, so I have my tension is equal to m2 times v squared over r. This one right here, I have y is equal to m2g. And for the last equation, I have tension is equal to m3g. I can now, I'm solving for speed.
For the M2 something, is that a 0 or the 5?
That's a 0.
Oh, okay.
It does look a lot like my 5s.
What's the next step?
Solve. Plug that into there.
Probably just.
So I have m3g equals m2 v squared over r. V therefore is m3g over m2 times r square root. And now plugging, bless you, so that's 3 times 9.8 times 1.5 divided by 2.
Oh.
But one of these days, I'm gonna nail it out that far. You'll see me do the happy dance, whether you want to or not.
Really?
Oh.
This sounds exciting.
Square root. Ah, you were so close.
What is it?
4.6957. And then more numbers.
All right, units.
Meters per second.
Stephanie,
What's the subscript on that y equals mg at the bottom?
that's a 2. Clearly.
Looks like an I.
Yeah.
Wait, so Dr. Fox, weight is not represented with a double, like, with a specific W, that's just how your W's look like?
I mean,
Yeah.
as in the textbook used the same symbol. That
No, it just confused me earlier, I thought the whole time that's what, but that was like on purpose, the little,
I put that there to different. I use capital W for work and watts. The omega got a pearl of both sides differentiated. The lowercase w put the little flare off to the right to make it look different from a capital W.
okay.
Or
And
maybe
the omega.
just
Well, like a textbook can't
Do
do that. So.
this instead of.
Yeah.
I wanna be just like
When we get to the P's, telling the difference between my capital and lowercase p's becomes very difficult at times.
Okay. Would you mind? Thank you.
All right, our first centripetal motion problem. Questions before I make it a little harder? Then let's make it look harder. So instead of having this on a nice frictionless table, come on. That won't fit. Oh, the pen is stuck. Oh, wait. Pencil. All right, so I have this stopper right here, and I'm basically swinging it around like that. So right now I'm holding onto it so I can swing it as fast or as slow as I need to. However, that's not particularly precise, so what I want to do is attach a mass to it. And this thing has been taped so securely.
Just use a stapler? Do you mean scissors?
I pulled that through there and attach the mass here. There we go. So I'll shorten the length. So if I just let go, in a frictionless world, this is clearly more massive than the stopper is. It's just going to go like that. So I can't maintain equilibrium unless, at least for this mass right here, unless I spin it. Now if I spin it, that's not in equilibrium, but the tension is equal to the weight of this. And so what I want to know is, well, what is the angle? How fast am I spinning it? What is the mass of the stopper? That's probably a good one. So I'm going to spin it until there's a little black mark on the string right here. And I want to know what the mass